Once again, we ran out of my ideal time for completing part 2, and I had to split it in half. So this is going to be the second half of part 2, or part 2.2. Here we go. But the second order ODE can be solved given values of the unknown function at two different values of x, which turns into boundary value problem. Now, when you try to trigger the boundary value problem, for some reason, there seems to be a bug. So when we activate the boundary value problem solution, we get this warning. I have no idea why, but all what you have to do not press stop at all. Press continue twice, and then you get the form that is required to solve the problem. Here we're going to be using the solution in solve for, the same that we obtained over here. Solution to a second order equation. But now we are going to do a boundary problem in which for solve for we put that x equals 0, y equals 1, and x equals 2, y equals minus 1, as indicated in here. Let me repeat that for you right here. Go equations, boundary value problem, continue, and there's the form where you type those results, and then it triggers this command. And when we press Shift Enter, then we get the solution where we no longer have the constants k1 and k2 that we have originally had. Instead, we have the solution with the values replaced in terms of the exponential square and so on. One thing to keep in mind, the constants come out with a percentage in front, sort of indicating that they were generated by the computer and not created by the user. Okay, so that's the boundary condition. Then the next step is Laplace transforms. Solve the ODE with a Laplace transform. Now, Laplace transform is used in signal processing, and it's such that if you have a function of time, the Laplace transform is an expression that will give you an equivalent function of frequency, S. And the inverse Laplace of the function in frequency domain will give you the original signal as a function of time. Details of the Laplace transform can be found online or any book on differential equations. At this point, I just want to show you how that works. And so, for example, if you say in the calculus menu, they have a Laplace transform and an inverse Laplace transform. A Laplace transform form where you can enter, for example, as I did in this example, sine of t, where the old variable, the original variable is t, the new variable will be s. And the inverse Laplace transform, it's triggered by using calculus inverse Laplace transform. Here's the example, 1 over squared plus 1, and that produces this ELT function, which when we do shift enter shows delta t. Delta is the so-called Dirac delta function, which is used in signal processing or control. And so these are ideas related to Laplace transforms. But we're doing is solution of ordinary differential equations. We type this equation here, a second order equation, and then we use equation solve ODE with Laplace. We'll trigger these. We'll trigger this form, and for example here we load ODE 3 and solve for x of t, and we get this solution. Now this solution is now given in terms of the initial condition x of 0, and x of 0, and the first derivative of the x and the t at t equals 0. And this is what the kind of result that you will get if you use the Laplace equation in solving your ordinary differential equation. And the next step would be store that into Sol 5. Oh, sorry. Shift Enter. Now that's stored into Sol 5. And we're going to substitute the given values. Now x0 is just x parentheses x of 0, whereas this derivative, it's written in this form. Let me type above here, add apostrophe diff x of t, comma t equals 0. The result that we get from this is precisely this term, which is this term right here. And that's where we type it right here, and we do replacing these values, x0 equal 1 and diff of t at t equal -1 in here, and the derivative in here, we get this result converted into this one. And that's how you would solve an ordinary differential equation using the Laplace transform and substituting the initial conditions. The last two options under equations, left side and right side. Basically, if you have an equation which could be a differential equation like this EQ1, the function's left-hand side, will give you the left-hand side of the equation, and the function right-hand side will give you the right-hand side of the equation. And that will be the end of this part 2 of the equations menu in the wxMaxima part.